So we have, I have two announcements. One is that please keep yourself muted during the talk. And the second is, as much as possible, we will take all the questions towards the end of the presentation, in order to make sure that the presentation stays within time. But Dr. Nico has agreed to stay back after the formal presentation and Q&A session. So if some of you want to have a chat with him after that, you are most welcome to do so. So with that, I will request Jaya to take over and conduct today's proceedings. Thanks, Jaya.
Yeah, thank you, Guru, and thank you so much, Nico, for agreeing to join us here and sharing your work and your experiences as a PhD student, and now later continuing at MPIE as a scientist. So before making a formal introduction, I have known Nico since 2015 or 16. And I have always seen him laughing like this. So there is a lot of common things between probably Guru and Nico. He's also known for his laughter here. And he's always been this cheerful, very helpful student around. And he also had an amazing work-life balance, and he inspired a lot of people to get into fitness. But besides that, and more seriously, Nico has been at the forefront of a lot of cutting-edge research at MPIE. Before that, he obtained his BSc and MSc in microtechnology and nanostructures from Saarland University, Germany, with an extended research visit at both Peking University, China, and Caltech in USA. So he worked with, he's gained a lot of experience during his bachelor's and master's. He then chose to join for his PhD at MPIE, Düsseldorf, with Gerhard Dehm. And during this process of his PhD, again, he visited the US for a research visit at the National Center for Electron Microscopy. So his research is focused on linking structure and properties of materials using in situ high resolution electron microscopy. So without much ado, I would hand it over to Nico to actually share all the work that he's been doing. Thank you.
Super. Thank you, Jaya. That was like one of the nicest introductions I had so far. Thank you so much. That was wonderful. So, and of course, thank you for the invitation, right? I'm super pleased and super honored to be here. Wait, this is actually the wrong screen that I'm sharing, I think.
You're probably sharing your entire screen, but that's also okay.
So that one should be right now.
Yes.
Yes. So, yes, I think now you should see it.
Yes, it's visible. Guru, are we recording? Is Nico okay with recording?
Yes. Recording started when I started the session.
Oh, okay.
So,
all right.
yeah.
All right.
We will edit out the initial portions and then.
Yeah. Sure. Thanks.
Perfect. So you can see the laser pointer, you can see the slides. All good?
Everything. Perfect.
Yeah, all set.
Super. So thank you, Jaya. Again, thank you for the invitation and thanks for having me. And I'm super happy to see you again now, a little bit more, involved. That's really cool. And thanks for the kind words, of course, from Guru and from Jaya. And yeah, welcome everyone. So I think today you are interested in grain boundaries, my work on grain boundaries, which is mainly my PhD work that I'm showing today. And I don't need to read the title. I think if you are here, you have read it yourself already. But first of all, I would quickly show where we are. Maybe some people don't know. I mean, this is India. You all know that. This is Germany. You probably may have seen it. So it's quite a long trip to go, but you can make it. There are planes. This is the beautiful city of Düsseldorf. I think in summer times, they have a lot of green inside the city. There's the Rhine River is running through with lots of nice bridges. So I think you can have a quite good life there. And then, of course, we are at MPIE, so the Max Planck Institute for Iron Research, which is shown here from an aerial view. There is 3 main departments at the moment, I would say, and they include Professor Dehm's department, where I am located at. This is white building here, which is mainly the microscopy facility, I would say. Then there's Professor Diagrabe's department, which is alloy design. He's doing a lot of alloy design, and we have all the ovens and all that stuff in here. And then we have a computational department at the entrance here from Professor Neugebauer. They basically complement the experiments, or we complement the simulations. Nevertheless, we have a very close interdepartment collaboration going on. So work here is quite nice, I would say. So without going any further into where I am from, I think people are interested in grain boundaries, and that's what I'm talking about now. So why are grain boundaries actually important? If you take your cell phone, you probably know it has a lot of copper interconnects inside, and they're getting smaller and smaller and smaller. And also with getting smaller structures, you probably also get smaller grain sizes. And if you do decrease the grain size, some of you might know the resistivity actually goes up. With increased resistivity, you might get some sort of pronounced Joule heating, which might lead eventually to electromigration. And this is just a thought experiment, which might then turn off your phone in the end, right? So, you know, decreasing the grain size actually also means increasing the fraction of grain boundaries inside your material. So there must be something going on. Another example, more on the mechanical side, is the well-known hole patch effect that says if you decrease the grain size, your strength of your material goes up. And then there's also something called like the inverse hall patch effect. If the grain size is getting very, very small, some people argue that actually this effect reverses and you decrease your strength of the material. So clearly, again, grain boundaries might need to play a significant role in this effect, because if only the grain size changes, also only the fraction of grain boundaries changes. Another example is the higher creep rate. So if you, again, decrease the grain size, you also increase the creep rate, which might also have to do, again, with grain boundaries. So there's a multitude of effects, and this is just some random ones that are related to grain boundaries, which make them, or these defects, quite important for our materials and how they behave. But now, what is a grain boundary? So if we take two grains, and everyone should know a grain is like a crystallographic orientation of the crystal lattice, and we take two with different orientations, and then we merge them, we end up creating a grain boundary at the intersection of both, like shown here, for example. And you can tell already this looks different from a perfect crystal. So, you know, we need to characterize this somehow. How do you characterize grain boundaries? Maybe a little introduction to that, so that we are all on the same page. If you take a geometric approach, which is pretty common for grain boundaries in literature, you just take one crystal lattice, you put a second one right on top of it, and then you rotate against each other about this point here. You will see at some certain rotations, you start forming coincidence side points. So what you form is like these red points here. So the green and the blue are the same position in this case. And this lattice then is called the coincidence side lattice, the CSL lattice. And now people like to characterize grain boundaries by a sigma value, which is the volume of this CSL lattice, the red points, divided by the volume of the crystal lattice, which is, for example, the blue or the green points. In this case, it's the same. So what we are talking about today, and this is just an example of this, is the sigma 5 grain boundary. In this case, you misorient, or you give a tilt misorientation. So you tilt your one crystal by 37 degrees. And what happens then is you form this dichromatic pattern. If you now take the grain boundary line along these red dots here, and then of course take away the blue dots on one side and the green dots on the other side, you form a grain boundary as shown here. And this is what we're looking at. There's also an experimental picture that this actually occurs in nature. So this is what we're doing or dealing with today, mostly. So there are other things that characterize grain boundary, the grain boundary normal, the rotation angle. If they are aligned perpendicular to each other, then we call it a tilt grain boundary. Or if they are parallel to each other, then we call it a twist grain boundaries. But for today, we also will only talk about tilt grain boundary in this sigma 5 system, because that makes it easy. If we look at this along this orientation here, then we see it's always the same. We only rotate the letters around this axis. So we have two axes in the two grains being the same, which is important for the electron microscopy study that we want to do. Like this, we can get high resolution images in both grains. Why this is, if you have questions for that, you can ask me later, please. So, okay, we said, well, there is an interface forming. That means we have a grain boundary structure, and associated with that, we usually have a grain boundary increase in energy, just because the perfect periodicity is disturbed here. So if we now plot the axis energy we versus the misorientation angle, meaning we rotate around this axis here step by step, we can plot all the grain boundary energies, and we see a plot something similar to like this. So at some points we have some cusps here, meaning this is like special boundaries where the energy is a little bit lower than it should be. It should be just a roundish curve. And these boundaries are special, and special are most often the actual sigma values. So these special boundaries that I described before, where we have coincidence points in the grain boundary. And today, as I said, we talk about the sigma 5. So we will be on this side on these 2 points in this plot here. So recently this is more or less textbook knowledge, I think, and most of you should be familiar with it, probably. Now there's a concept that has been exploited by Hart already in the 70s, who said, well, a grain boundary can also undergo transitions. So he postulated, or he thought that if you look at the grain boundary energy versus the temperature, you will have at room temperature an alpha phase that exists of some sort, whatever it is. And then if you increase the temperature, at some given temperature, you might change to a beta phase. So the grain boundary itself undergoes a transition, basically. And this transition can have multiple, facets, so to say. Not facets in a sense that you form a grain boundary facet, but it can have very different appearances. So this concept was then experimentally kind of shown in a paper 2013 by Tim Frolov, who showed that the diffusivity of a grain boundary with increasing temperature changes. And this diffusivity is actually silver atoms in a copper matrix or in a copper grain boundary. So increasing the temperature, eventually this slope changes. And as this is an Arrhenius plot, the slope shouldn't change. So this change is unexpected and was attributed to a change of a grain boundary phase, so a transition. And then he performed some simulation experiments and could reproduce this. So he found actually two phases that have a coexistence point. So there is two ranges where two different grain boundary structures exist, and how these look like are shown here. So this is the sigma 5 grain boundary as I showed it to you before, with silver sitting at certain positions. And then there's the low temperature configuration. And then if we exceed a certain temperature, we actually form the split kite, or he called it a split kite structure, where the grain boundary structure changes. However, the plane remains the same. So this was more or less the first prominent example, I would say, where people were finding these transitions. And since then, they have been exploited quite a bit. So as I said, these transitions can have different appearances. For example, we can have a congruent transition where the structure of the boundary changes. However, the plane remains the same. There could also be other, like incongruent transitions, obviously, like a faceting transition, for example, what I'm going to talk about today, where we have an initial grain boundary which decomposes into two segments with most likely a defect here at the junction of these two facet segments. So people in the 80s performed a very nice experiment in situ in the TEM, where they had a copper grain boundary and put bismuth inside. And bismuth is known to embrittle the material very much. So if you look here, you can see a nicely faceted grain boundary state for a high bismuth concentration at the grain boundary. And then in situ, they were able to extract bismuth from the grain boundary, switching it back to a flat grain boundary, and then again putting bismuth inside the TM in the same grain boundary and reproducing the faceted state. So this is a very nice and very unique experiment in literature, However, it also opens up a lot of questions because at the time the resolution was not quite there yet to have, for example, atomic information, what is going on at different sites along the grain boundary, and so on. But besides this experiment, there is not much work actually on chemically induced faceting. There's a lot of work about temperature induced faceting, but there's not so much about chemically induced faceting. And then for this exact case, Ziegler actually came up in 2002 with a mechanism who says that, well, at high temperatures, there is some bismuth at the boundary. And if you cool it down, more bismuth goes to the boundary, eventually exceeding a certain threshold to form a facet, a little facet which is decorated in bismuth. And then more bismuth decorates the entire boundary, saying that the whole boundary is decorated in bismuth. So maybe you can remember this a little bit. I will come back to this at more the end of the talk. So this was the picture people had so far, kind of. But now what is missing? So this is more or less the questions that I tackled in the work and that you will probably see now in the next half hour. So first of all, the atomic structure of grain boundaries is very hard to read experimentally because it's so small. And because even in electron or transmission electron microscopy, for example, you need to have very special conditions for the grains to be oriented in a certain way. Second of all, grain boundary transitions are even harder to observe at the atomic resolution because usually that involves some atomic shuffling or whatever, something is moving. So you have to have a very well-controlled experiment and a very well-controlled machine to observe that actually. So drift, for example, at the lowest rates might kill your experiment. In TEM, for example, a little vibration might kill all your images. So what has become very popular at the moment is to establish phase diagrams. And this is not a phase in a sense like we know phases like bulk phases. This is a grain boundary phase. So two-dimensional object, which makes it a little different. However, people try to establish phase diagrams saying at certain temperatures or at certain solute concentrations, certain phases of a grain boundary exist. And this has become very popular. People are putting a lot of work into this and finding by simulation work mainly a lot of interesting things. However, segregation-induced faceting, there is not really much, as I mentioned before. So there's a lot to learn maybe even in this case. Also, as I mentioned before, in older work, there was not really the resolution yet to observe such phenomena at the atomic scale, what is actually needed to understand them and the mechanism. So the mechanism by Ziegler, for example, was built purely on, let's say, SEM and conventional TEM studies. But we can now confirm that experimentally or not confirm it, however it comes. And then what is completely missing to my mind, or not completely, but mostly missing, there's very few examples of how can we now connect these transitions that we find to physical properties. Yeah, because in the end, we want to know, well, does that matter for constructing materials or does it not matter? And I tried to give you some recent experimental results here where we tried exactly that. So that brings me to the outline of the talk. In the first chapter, I would like to introduce the induced grain boundary transition that I observed. In the second one, I would like to show you a little bit if we change now the concentration of solute at the grain boundary, how does the transition change? Then I would like to go a little bit more in depth, like, okay, can we actually determine inside the grain boundary how solutes are behaving inside there? And at the end, as I said, I would like to go a little bit into the relationship between the structure and the plastic deformation. So how did I fabricate my grain boundary? And I did this with a modified Bridgman method. So you do have a polycrystal, like shown here. You put two single crystal seed crystals at the bottom, and then you heat it up. So you have a polycrystal that then slowly becomes a bicrystal. This black line here indicates that. From there, how it looks experimentally in real life, it's shown here. We have the two seed single crystals here, and then we have the bicrystal with the grain boundary running fairly straight here with two common 001 growth directions or zone axis later in the TEM. And what we formed is an asymmetric tilt grain boundary in the sigma 5 system, meaning that the rotation of the two grains, as I said at the beginning, is not symmetric, what many people observe at the moment. It's asymmetric, and we did this on purpose to actually be a little bit more realistic, because symmetric boundaries don't happen too often in real materials. So from this bicrystal, I cut some pieces, some cross sections, and used 3 different states to then observe and make my research on what is happening. So first of all, we have a silver-free bicrystal, and this is a cross section through the bicrystal. We then take one of these and just anneal it for very long, 5 days at 800 degrees C and under high vacuum, 10 to the minus 6 millibars, which is the annealed reference state, so to say. And then we use silver to also trigger our transition, as was done by Tim Froller, for example. So we sputter deposition silver on top and on the bottom of such a bicrystal, and then anneal under the same conditions to have it segregate into the boundary and along the boundary. So if we then, after that, look at the boundary, we can see, well, it is a fairly straight grain boundary on the macroscopic scale in conventional TEM. But if we zoom in now to atomic resolution, we see the as-grown state is still fairly flat. It has a little roughness, but overall we call that a flat boundary. The annealed case is pretty much the same. Nothing changed really. So annealing without chemistry being involved doesn't really change much. But if we then introduce silver, we do see pronounced faceting occur. And this is shown here. We have a boundary that runs in a zigzag way. And what we can see here is also, this is preferential segregation. So one part of the facet is silver free. One is decorated with silver, and you can see it by these bright dots. So these are HADF Z contrast images in STEM. And you can see all these bright dots are a higher Z number material, which is likely the silver. And we can also look at the structure. So we find that we have an asymmetric nanofacet here, and then we have a symmetric 210 facet here. And this one is the boundary that I was talking about much before, which is a very common boundary, the symmetric 210 boundary in the sigma 5 system. The structure is shown here a little bit more in detail, and we see the silver always falls in these central CSL positions, as I mentioned at the beginning. The asymmetric segment is a little bit more confusing. It's not so clear to how exactly the atomic structure looks like. This is related to, at the grain boundary, atoms become fairly mobile under the conditions we chose in the STM. Anyways, it's just a really complex structure, how it's supposed to be for an asymmetric boundary. And the planes can be seen here, so it changes from a 110, 410 boundary into a faceted 230, 100 boundary and the symmetric 210 boundary. To confirm that this is actually silver at the boundary and not just saying this is bright and not so bright columns, we did atom probe tomography, and we can see here, well, we do have certainly silver segregated to the boundary and mostly to the boundary, how it's supposed to be after the faceting, the phase diagram of copper silver. We can also see this in the concentration profile, that at the boundary we get about 3 to 4% of silver accumulated. And then from atom probe, we can also say the number of silver atoms is actually 2.76 atoms per square nanometer, which is the silver solute axis that we could determine here. And this fits very well to half a monolayer. So if a monolayer of silver would be decorating the 210 boundary, we would have a doubled concentration. So since we have a preferential segregation, as I explained before, this fits fairly well. What we also see, if we take a cross section through there, we do see that we do have this faceted behavior of the boundary as well as we saw it in STM. So confirming this also. We then performed a little bit MD simulations, actually Monte Carlo MD hybrid simulations to see coupled with STEM image simulation now. So these are simulated STEM images Can we reproduce this? Is this something we would, think of in terms of theory? And indeed, we do get this. We have a little roughness associated to the boundary, but if we look at it, it looks very close to what we find in the experiment, which is nice because it confirms our experiment kind of, or in the other way around, we confirm the simulation now. And if we introduce silver now, these are the blue atoms, we see pronounced faceting again of the boundary. And if we simulate that, we also see the faceting. We also see that silver mostly goes into the special locations in the CSL positions, as I mentioned before, similar to what we observe in the experiment. So this also reassures what we are doing is quite right. We also looked at the asymmetric part, and here it's a little bit different. So the asymmetric part can take up silver. However, it does it in a very linear way. So there are very long lines at certain positions along the boundary, and we chose a boundary very close to what we have, of course. And in between, there are usually gaps where no silver likes to go. And apparently, our asymmetric segments here make pretty much exactly that. So they are usually about a nanometer in length, and this fits very much to this gap. Why this gap likes to be there or not some more silver, that's a question that I cannot answer. But yeah, I'm happy to discuss this if some of you has a good idea about it. We can also look now how much silver can the grain boundary take up. And there's one, the asymmetric boundary takes up at a low chemical potential, so meaning there is little silver available. The asymmetric boundary can take up already a lot of silver, while the symmetric one does not. But once the symmetric one is there and the concentration is high enough, it takes up silver very much, and much more than the asymmetric one. This is also reflected in the grain boundary energy degrees from that, because if once the symmetric one takes up silver, the energy goes down very rapidly compared to the asymmetric one. So that was a nice observation, which kind of explained a little bit to us why we see certain features. So why is the silver mostly going to the symmetric portion of the boundary? It's just energetically much more favorable once they are there. So that means also it's likely because we just initiate this or we form these because it's energetically much more favorable. Still, there are some questions. For example, why is it not just forming a long line full of silver? And this we try to answer now in a follow-up experiment where we looked at the concentration dependence. And what we now did is we took a bicrystal again, with red being the bicrystal and the straight grain boundary running down here. We put silver on top and have it diffuse in under the same conditions as before. And what we see is in a cross-section now that from the surface down into the bulk, we do see that the grain boundary moves. So it curves away towards the surface. And what we could find, I wrote it down here already, is we have an asymmetric boundary, we have a faceted boundary, and then we have a symmetric boundary. So the boundary changes depending on the silver concentration that we have. And this is shown here. This is the initial boundary, which is straight. And then at the end, it curves away towards the surface after the experiment. And of course, these are not rotated. These are, of course, in the same orientation. So from the bulk, where we have lowest silver, we have more or less our reference boundary with bright, silver that I mentioned before, distributed along the boundary. And then eventually we start coming into the faceted state, where we form facets that are decorated with silver again. And towards the surface, one facet segment, the silver containing one, grows in length. So it becomes longer and longer, while the other one remains more or less straight. So at the very surface, then we finally find our long straight line here, which is quite interesting because then, faceting is no longer observed. And this is again our 210 symmetric boundary that I have been talking about quite a lot. Again, we did some APT measurements. Again, we find silver being segregated only to the boundary. We also found for the one tip that was closer to the surface, a straight boundary, and one deeper into the material, a faceted boundary. And also we could observe again our enrichment at the boundary with a depletion zone close to the boundary until it reaches in the bulk somewhere again equilibrium or saturation value of silver. We characterize now our silver inside the grain boundary with EDS, and that has a certain reason, because APT, you cut out a needle, you don't really know where you are in depth. That's pretty hard to determine. If we just cut a cross section and look at it at TM, we can locally be very precise where we measure our concentration. And very precise means at atomic resolution. So this is now what we did here, and we did this for the symmetric portion at the surface, which is the gray with highest intensity. We did this for the nanofaceted case, and we did this for the asymmetric case. So we plot here only intensities because we did this in zone axis. And if you have an atomically resolved image where you see a nice crystal structure, be very careful about the EDS quantification. That does not really longer hold too much. So we preferred to go to collapse this and then talk about fractions of a monolayer, because we know for a monolayer, we have our very surface case, that's a monolayer of silver more or less. And from that, we know the concentration and relate all the other intensities that we found. So in this, we could see an increase of silver in terms of monolayer concentration at the boundary. And I think this makes much more sense in this case. So what we could also observe then is, I said one segment is growing, the other one is not. So we could establish a faceting diagram where we say, well, at a given value, we have an asymmetric millimeter long boundary, but no symmetric portions. And after this transition, we start having a more or less 1-to-1 ratio between the two facet segments. And with increasing silver at the boundary, we linearly increase the length of one facet segment, the silver containing one, until we have a micrometer long symmetric boundary towards the surface and no longer an asymmetric segment at all. From this, we were able to construct this diagram here, and this gives now the facet segment ratio, and this is basically the symmetric segment length. So how long is a segment of the symmetric silver containing stuff in relation to the entire segment, to the entire facet. And this is what we plot here against the coverage again, so the concentration if you want. And what we do is we take a red line from the very surface where we assume monolayer coverage, which is 100%. And then at 0, we should be at 0. So if our facet segment ratio is 0, we have no symmetric silver containing portions. We should have no monolayer at all anymore. So this is this red line here. And then we measured, of course, different points at different facet segment ratios and fitted them and found that the agreement is fairly good. So that means that actually the silver concentration linear decreases with the symmetric segment length. That means also that our assumption means that the monolayer is pretty much always at the symmetric facet segment, while the asymmetric segment is almost always completely silver free. And then there's a third portion of this graph that is interesting. At 0, so we have 0 symmetric segment. This is the asymmetric boundary. We see it has 30% silver. So it takes up silver as expected from the simulations also, but much higher than it should be. And then suddenly it jumps to 50% and does a faceting. And this jump here indicates a little bit that this actually is a first order transition that we observe in this case. So finally, I would like to also jump a little bit more in detail how the segment or the silver containing segment looks like. And for this, we did some in situ work at the stem, where we acquired 200 raw images, which are shown here, so you cannot see much. We averaged then 4 of them to get a little bit more the feeling of how things are related to the image. And you can see already here again the bright columns. And then we zoom into these and make an animation out of that. And now I think I need to switch back, yes. And here you can see how, how the dynamics of this facet segment is. So this is 10 frames per second, and you can see 3 columns containing silver changing in their intensity. So we extracted here the actual peak ratio, so the intensity peak ratio, how much intensity we have in the bright column here. Oh, should switch back again. How much intensity we have in this column here versus the bulk. And this is related to the HAADF Z-contrast imaging conditions, then correlated to the atomic column occupancy. So how much silver is in one atomic column at the grain boundary here. And we see the blue column being very constant, while the other ones fluctuate a lot. And also, if you look at certain positions, for example, here, if one goes up, the other goes down. So, you know, they are opposing each other. So that means if we sum up all the values, it's more or less constant. And that again means that silver is pretty much staying in the facet and doesn't like to go out or doesn't like to take up more. So once the facet is there, it's pretty stable. And this is now no temperature, this is just induced by the electron beam. We give energy to the grain boundary by the electron beam, 300 keV. How can we relate the peak ratio with the occupancy? Well, we do image simulation, quite a lot of image simulations where we have our MD cell or an XYZ file where we build the grain boundary based on our experiment. And then in these CSL points that I explained before, we put in silver to 25%, 50%, 75%, and 100%, which is a full column. And then we look at the peak ratio, and we see that they have certain curves. And actually for a 100% silver, so a full column, we see that this matches very much the peak ratio value that we find in experiment for a 30 nanometer thick sample. So this is also the thickness of our samples that we typically observe. So that makes sense. So this is how we relate, okay, this blue column that I showed before here, this is actually 100%. And based on the rest, we can then have a scale of how much silver there is in the column. How we did this, in situ stuff, I would say, is we took 200 frames and then we did a moving average approach so that we take the first 4 images and then take image 2, 3, 4, 5, and then 3, 4, 5, 6. So in the end, we end up again with 200 frames. We can now also do a different approach where we've been in the time domain saying that we take 4 images again, but then these 4 images form one image. And then the next 4 images form the second image. So we reduce basically from 200 frames to 50 frames. And if we analyze this, then we see, well, there's a complete collapse of the signal. We cannot make any anything, or we cannot extract any meaningful thing here out of the data. So if you like to do that, always keep in mind that in TM, things are pretty mobile and move around a lot. So you need to have pretty high frame rates to do such things. Okay, so I think with this, we have everything together to postulate more or less a mechanism that we think is happening for the copper silver case. I showed you before the copper bismuth case here, and we can, as I said, they think at some point a facet initiates and then silver goes and decorates the whole thing and these facets form. We think a little bit different. We think that at high temperatures, we have the grain boundary and silver in solute solution with higher concentrations towards the surface. So the right side is the surface, this is the bulk. So if we cool now, all the silver slowly starts going towards the boundary, segregating towards the boundary at higher concentrations at the surface to lower concentrations in the bulk. And then they initiate the facets because it's energetically favorable to initiate these 210 segments. You know, they take up more silver, they lower the energy further, so it makes sense to nucleate them. But because of that, you need to introduce also a second segment, which is this asymmetric segment. And this one is constant in size. So it is more or less a kinetic barrier, what we believe, that defects that run along the boundary to form these silver decorated segments cannot move further. And the result of this is basically the more silver we have, well, the longer and higher frequency of segments we have, but the less silver there is, the lower it is, and the less frequent they come. So this is why we have this decrease in length, and therefore inducing this curvature to the boundary. So we don't think it's, for example, grain boundary induced migration. And why is this? Well, we think it's because different things. We have the grain boundary here schematically with no silver and silver containing segments and the junctions. And if you look at the grain boundary energy change, it is related to the asymmetric portion, the symmetric portion, and the junctions. So this portion here is the main contributor, because here silver goes and changes the energy, minimizes it. This portion here, we don't have any, silver going there, so it's not changing the energy there. However, it is, yes?
If I may interrupt you, it's gone up from the full screen, at least to me.
Oh, it's gone from the full screen?
Yeah, to me too. Yeah, it's showing your notes.
Just this previous slide. So.
Okay. Let me check. Is it maybe back?
Yes.
Ah, perfect. Okay, I know why. That's good. Okay. All right. So, perfect.
Oh, it's gone
Thanks,
back
Jaya.
again.
No, Nico, it went back. Yeah.
It went back? Okay.
Right.
Oh. Now back again?
Not yet.
Not yet?
When you probably pressed escape, it did that and then went back.
That's very strange now. Sorry. Try again. Nope. Oh, this is now very strange. Ah,
Now
it should work.
Yes.
Yeah.
Okay, I leave the laser pointer for now. It seems to mess
right.
things up.
Okay.
Okay, anyways, so this is maybe the point here that is needed for the decomposition, as I said, and acts as a kinetic barrier. And you can see here on the graph, this is some simulation work from previous people, and it shows the blue curve, the dotted curve is if you have a G factor, which is a purely geometric thing and is 1 for the symmetric boundary, the 210 boundary, which says this is 210, this is 210, so this gives a normal number. It's a very smooth decrease, so the facet period wants to increase, so you want to form a very long boundary. If this is now an irrational number, like square root of 13, which is the case for us here, it becomes very jerky. And that means it comes to very high energy barriers locally, which act then as the kinetic barrier. And the junctions are negligible here due to the kinetic barriers that we actually observe. So finally, I would come to the chemical or to the plastic deformation part. And this is very new results. As I said, this is not yet published. So to give you a little bit idea how we're going to relate the things to each other. So this is how a TEM holder looks like. To give you an idea, this is how we put our sample. This is not the sample. This is where we put our sample to observe it then. And here is what happens. If we have the pure copper grain boundary and we do a dog bone shape and deform it under tension, we form these deformation features. And typically we form 1 or 2 small ones, and then one grows in size very long. Okay. We also observe that the width of the grain boundary decreases. We have very defined orientations, which actually coincide with the 110 orientations from the crystallography, which is nice. Because that means, okay, this is more or less related to slip in copper, right? So if we now take the sample and compare it to a copper silver sample, we see, well, we have a lot of these features now forming along the boundary until a certain point, and then we have nothing forming anymore. And this is up here the surface, and this is down here more towards the bulk. Also, we don't have this long extended features like on the left side. So we know from our experiments before that on the top towards the surface, we have high silver concentrations, and to the bottom, we have the less silver concentration, the nanofacet case. So apparently, the 3 states that we have differ in what happens under deformation conditions. So again, we did some simulation work here for the straight grain boundary, the reference grain boundary, the pure copper grain boundary, and then the FACET's copper-silver grain boundary, and performed also the deformation under the same conditions. And what we see is, well, on the one hand, in pure copper, we form these long extended features, while in the copper-silver case, we form a high density of these small features. And I have to say what they are. Some might have already the guess that these are stacking faults. So we have some during in situ deformation where we can observe they come out of the grain boundary. So it seems we have stacking fault nucleation from the grain boundary into the grains. This is the contrast given here, the stripe contrast. And here we even see the leading partial coming out. We also confirmed this by stereographic projection here, that we have the nice mirror symmetry of the reflections. And then to confirm or to prove to you that this is happening, we also performed a closer look in MD simulations. And here you see that partial dislocation is coming out of the facet junction. So apparently the facet junction is the point that is of importance here and makes the nucleation point. So hopefully you will see the video now playing. Yes, so here from the facet junction, we have a partial dislocation coming out. And with this, I'm at the end of my talk. I think 45 minutes are pretty much over. So what do I would like you to take home from my talk? And this is two main points. Point one is, well, we can induce faceting transitions and have preferential segregation at the grain boundary. And this is shown here very schematically. So not only is temperature a point that is important when it comes to deformation, like segregation obviously does also play a role. And especially since now we can have a high resolution point of view on these grain boundaries, we should think about characterizing our grain boundaries much more in detail if we see, for example, curved boundaries. You know, not necessarily, I think every curved boundary necessarily also just needs to be curved. It can also be, under certain conditions, be a faceted boundary. I'm not saying that that always happens, but I think we should pay more attention to characterizing our boundaries or microstructures in more detail. And the second thing is, well, we do see that chemically triggered transition of our grain boundary actually can have influences, and this is just initial results, on the plastic deformation behavior. So a chemical effect can have a structural change that influences the mechanical properties by, for example, forming more nucleation points for stacking fault emission, for example. And why these form, if you're interested in that, I would leave that for the discussion part. With this, I would like to thank you all again for coming, for listening to me. I hope it was clear and not too confusing for you. I would, of course, thank my group that was helping me in all different regards, obviously, for the invitation again. Super nice to have this chance to talk to you and have a fruitful discussion and maybe share some experiences, your attention. And I think it's always good to end with a nice sentence that someone said before. And coming together is a beginning, keeping together is a progress, and working together is a success, as Henry Ford said. So with this, I started working with these guys. I got in touch with you guys. So let's keep it up. And yeah, thank you very much. I'm looking forward to your questions.
Thank you so much, Nico. It was a great beginning and a great ending as well to the talk.
Thank you.
I really enjoyed it. It was very clear and very systematic. And I think you took us from the beginning of understanding grain boundaries in a very basic way to all the way into a very sophisticated understanding of it, which I'm sure some of us wouldn't be able to follow fully, but we would, be, I think, encouraged to go back and read your papers and maybe ask questions right away. So,
that's super nice. So mission accomplished, I would say.
Yes, Guru, you want to go with the first question?
Yeah, I have a series of questions.
Okay, that's fine.
The others, please raise your hand and I'll call you out when you're up
So
for it.
I
Yes.
have a basic question. In slide 7, the two sigma 5 boundaries did not seem to have the same energy or the same kind of cusping. Is that correct?
Slide 7, you mean this one?
The sigma boundaries, the sigma 5, two sigma 5s.
Yes.
Why is
actually
that?
That's actually true. That is because they are actually different boundaries. So there is a sigma 5 symmetric 210 boundary, and there is a symmetric sigma 5 310 boundary.
I see.
So their structure is very similar. They form these kites. And I can maybe show you an example on the slide before. So here, here, I hope you can see now the laser pointer again. So this is a 210 boundary. So these kites are connected next to each other. The 310 boundary has another connection. So it's not, they are not connected directly, but by a little linear piece. So they are separated a little bit. And this little thing makes a small change in energy, which is not too pronounced, but it is there if you observe it very much in detail as you did, which is good.
So I also had another one in slide 18. So what are those white lines apart from the boundary that we see?
In slide 18, you said?
18, yeah.
This
yeah,
year?
the leftmost figure, I see some lines apart from the boundary.
Yes, so I have to say this is a STEM image again, HADF image, and these lines are dislocations. Oh, this is actually, sorry, that's not a HADF, this is a low angle annular dark field. So it highlights strain contrast.
I see.
And so dislocations and the grain boundary appear bright. That's usually nicer to show because you actually see the boundary. Otherwise, you don't really see it too much.
And silver segregates to these dislocations also?
That's now a very good question. I have not looked into this. I was involved in a project that did the opposite, that had silver and then had copper segregate. And there we saw actually copper segregate to the dislocations. Yes. If this is the case here, I have to admit I have not looked into it. It could be, I'm a little, I don't know, because you know, silver is a pretty big atom compared to copper. And I think it depends a little bit on the dislocation core, how big it is, if silver is easily fitting in. But in this case, dislocations are very close to the boundary. I would think it's energetically much more favorable to go to the boundary than to the dislocation.
I see. Okay, Jaya, is it okay for me to ask the last question?
Yes, please go ahead.
Yes, okay. So it is still not clear why they segregate, because there could be interfacial energy arguments that having silver on certain boundaries lowers energy. There could be interface stress arguments that this 2D grain boundary is having a different elastic property. So it is softer, for example, then it can undergo an instability like ATG, because your last movie was more like that, it's undergoing buckling. And it is also possible that because of elastic strains that come from the size differences, that there is this kind of breaking up of the boundary that is happening. So what is the basis of this sort of breakup?
Yes, so you brought up some very good points actually. In terms of, you know, how the elastic properties change and things like that. I believe it's not so much of a problem, because if you look actually on this slide here, if you look at the structure of the asymmetric boundary, it is pretty, I don't want to say chaotic, but it has quite some room for adopting silver, for example, for bigger atoms, right? So I think the strains that you introduce might not be as severe as if you look for this perfect boundary here, where, you know, you replace distinct atoms on certain sites. There it might be more severe. So I think initially, when we have a flat boundary and silver segregates to the boundary, the elastic portion or the elastic cause might be neglected for us. I think so. I'm not saying this is a proof. However, if you then, you know, as we said as we saw in the simulations, so silver is taken up by the asymmetric boundary, and eventually it is just more favorable for the boundary to have a 210 orientation, to take up more silver and to lower the energy further. What I didn't maybe say clear enough is this asymmetric boundary is not too far away from the 210 orientation. you can see maybe from this orientation here to this orientation, this angle here is fairly small, right? So the change in inclination is not too big to be an energetic cause, to have an energetic cause behind it, rather than you know, strains and things like this. So what we believe is indeed that the boundary takes up silver until a certain point, and then eventually it starts forming these facets to take up even more and then lower the energy further. Does that answer your question?
Yeah, and 210 has a higher energy compared to 230, that it would prefer to have silver there to reduce its energy. There.
Yes. So indeed, the faceting obviously increases the length of the boundary, which is first of all not wanted. But if it can take up more silver for the 210 facet, you know, growing in length even more, the more silver there is, then eventually it becomes again better to have the longer boundary, but then having it broken up in several pieces that lower further the energy.
And the MD simulations show this process of how this step moves to leading to the lengthening of these 210s.
No, unfortunately, we don't have that simulation. So the problem is, so you can do MD simulations, right? And simulations, molecular dynamic simulation, give you a very good sense of the structure. So small movements of atoms, for example, and all that can be nicely simulated. If segregation comes into play, that's on a very different time scale. So you need much longer simulation runs to actually have silver diffuse. And this is what is needed in the simulations.
You need some grand canonical Monte Carlo or something like that.
Exactly. And that's what we did. So for the segregation part, we coupled it with Monte Carlo. However, there the problem is we can only take snapshots at each moment, but cannot, you know, see the live video, so to say. So that's the dilemma.
I see. Yes. Okay, thanks, Nico. It was wonderful. So sure. Maybe there are others who want to ask. I will have a separate chat with you sometime. So
sure, no worries.
Yeah, Arjun, do you want to unmute and ask the question yourself?
Yes. So I'm wondering if the angle of the facets formed is a function of the solute atom, the radius of the solute atom in comparison with the matrix.
Okay, I'll read it out because his voice was not clear. He's asking, will the angle of faceting at the boundary be a function of the type of solute atom or the grain boundary angle as well?
Yes. Yeah, that's a wonderful question, actually. So I think the angle that I was giving here, this angle right here, is very specific to this specific case in terms of this boundary and this solute element. If we take a different boundary initially, which is further away from the 210 symmetric part here, for example, that might be a very different story, because then it needs to incline much more to get to the symmetric boundary, for example. And the symmetric boundary might be favorable because it itself has already a lower boundary than all the boundaries, asymmetric boundaries that are around it in the energy landscape. So I think it's mostly a function of the boundary type that you have initially. I don't think it's too much a function of the solute that you have, because the solute mostly goes to fairly defined positions, and most likely for the 210 boundaries, this is the CSL position, this bright position, for many elements that has been shown by now. So I think this is not really the determining factor. I would rather say the grain boundary is the point which makes the angle. Is that okay?
Yes, Arjun, do you have any follow-up to that?
Yes. So is my voice better now?
Slightly, yes.
Yeah. So actually, I was thinking of the solute in terms of the preference. I mean, if the solute radius is different, would it prefer the asymmetric side as well, instead of just sticking to the symmetric side of the facet?
Yeah, That could be, that might be, if you have a very, very big atom. But I mean, you know, the Z number of silver is, I think, 47, yes, and copper is 29. So if you go to really big atoms, maybe gold, but I think for gold, it has also been shown that it goes to these positions. However, really not so many people look at the asymmetric boundary. So it could be that the behavior of the boundary that I showed, maybe in this slide, where is it now? Yep. In this slide, that it forms these extended segregation pattern, like line segregation patterns, I would say. It could be that for different elements, this is different. That I don't know. That would be probably interesting to look into. We didn't go further into this so much, but that could be, yeah. So, but then your question is more related towards the preferential segregation. Is that changing? Maybe, and that could indeed be a function of the solute.
Yeah.
Thanks.
Nikita, do you want to ask your question yourself?
Yeah, am I audible? Otherwise,
Yes, yes.
yeah. So, a great presentation. I really like the work. Actually, I have a question. It's a very basic question that, as you suggested, that we creating a grain boundary using a polycrystal and a single crystal seed. Like if I do that, and if I cool down the metal and reheat the metal to the similar conditions, will I end up with a similar structure of grain boundaries? I'm curious about the reproducibility of the structure of.
Yes. Also
Is
nice.
my question clear?
Yeah. It's clear. That's also a nice question. I think this method here, for me, is more like black magic. So not in the sense that it's not reproducible. You can, you know, if you think about it, you can set it up in a way that it should make more or less the same all the time. However, you will, for example, not get a straight boundary straight off the top. For example, you can see here, there is some curvature of the boundary inside the crystal. So if there is something going on, you don't really have control over it. So this one functioned very nicely because the growth directions of both crystals is the same. So that means, you know, it's not very different how the crystal grows. It does the same on both sides. So the grain boundary does more or less stay straight. We also group grain boundaries in this way, where we had two very different ones, growth directions. And there it often happens that initially you form the boundary because, you know, the seed crystals grow, they crystallize, and then they meet. And at the middle, of course, they meet where else. But then growing it further, they just run out towards the side. And this is probably related to different surface energies of the two different crystals that we use or whatever. So this is then, if you have very much changing growth directions, it becomes pretty challenging for us to predict, especially what happens. Once you did it, you know it, and it happens most of the time again like this. But to predict it is pretty difficult for us. I have to mention, we are not really the experts in this. So we do it in-house, but we have an old machine and it's only one technician who does it occasionally. So if you would go to a company who does nothing else than that, you know, they know how to reproduce it all the time and they give you much nicer results probably. Also, there's other methods how you can prepare these bicrystals, maybe in a more defined way, like diffusion bonding. However, we don't know how to do that. There are only very few groups in the world who know how to precisely, you know, get a very straight line in the exact orientation, however you like to have it. So yeah, I hope that answered your questions more or less, and I hope you didn't get disturbed by the phone.
Yeah, I think I'll read the paper, and if I have any queries, I'll just mail. Thanks.
Yes, if you're interested, send me an email. I think that, you know, Jaya can provide it, or I can provide it later, or write it in the chat. I can send you some literature on crystal growth with this method if you want to. That's not a problem.
Yeah, that's great. Kevin, you have a question?
Yeah, am I audible? Yeah.
Yes.
Yeah. So I had a question on the APT you had shown on slide 19.
Yep.
I want to know how you are taking this distance measurement. Are you using a proxygram or are you using a 1D concentration profile?
You mean for this one?
Yes. The distance it's showing. See, my doubt is, let's say we are taking a proxygram. We have this interface, right? From
Yes.
there, we are taking the atom distribution. So
Yes.
that is basically a 3D structure that we are having. We are converting it to a 1D line profile, right?
Yes.
So where according to that is the line, or where is that line coming from? The 3D, how is it converted to a 1D?
Yes, so the good thing is in atom probe you detect individual atoms, right? So there's a certain loss, but in principle the 3D information gives you or the 3D gives you all the atoms that are available that have been detected. So this 1D profile is taken from a cylinder. You always choose a cylinder which contains a certain amount of atoms, and from this cylinder basically you then calculate, okay, how much atoms are silver, how much atoms are copper, and from this you calculate your 1D profile, if that answers your question.
Yeah, so you're telling basically to go for a cylindrical region of interest and convert that, it's averaged out, is it?
Yes, exactly. So this is why there's also scale bars or error
There's an
bars.
error bar, yeah.
Yeah, exactly. Because there is some uncertainty obviously associated to that.
Yeah, so would you suggest to go with a ROI, that cylindrical region of interest, or a proxygram? Which would you suggest if you want to show a concentration profile? Because both of them does show, yeah.
Yes, that is now a very good question for an expert, and I have to say this has been done in collaboration with some experts.
Okay, so fine.
So I'm honest here. I don't want to recommend you stuff that in the end doesn't hold a good choice.
Yeah. Okay. So could you just go to the slide before those HADF images that you have shown?
Yes.
Are these stigmata corrected HADF images that you are showing?
Stigmation, so these are aberration corrected, yes. So this is high resolution, aberration corrected high resolution microscopy. And then also these are averaged images. So we took a set of, I think, 20 images and then averaged them. And also, I don't remember if for this one, I think we did a registration of the images as well to align them on top of each other.
Sir, I lost you in between. My net went off. Could you repeat it? Sorry.
Oh yeah, no problem. So this has been indeed an aberration corrected microscope. So this is aberration corrected images, and also we collected 20 frames for each image, and then averaged the images and registered them to each other, basically to ensure that the positions of the images are right.
Okay. Yeah, the images look really good. That's why I asked, because unless you get it stigmata corrected, I don't think you can get such spot resolution.
Yes, thank you that the images look good, first of all. Second of all, I think you can, in an uncorrected microscope, if you choose the right zone axis, get some sort of atomic resolution, not in STM maybe, but in TM.
Okay.
So that should work. However, it depends on what you want to do with it. And TM then becomes a different story because you would need to do image simulation because of contrast reversal. So there is a lot more things to take into consideration.
Yeah. Okay.
But if you have a good conventional TM, I think in certain zone axes you can also get some okay image.
Okay. Yeah. All right. Thank you, sir. Yeah.
Yeah.
Oh, maybe I should add.
Go ahead.
For the grain boundary, that becomes a little bit more tricky, because if the two zone axes are not exactly met, then basically all the structure of one side disappears, and then you cannot make any any guess anymore of the structure.
Yeah, one side becomes clear and the other doesn't. Yeah.
Exactly. So this is a very high like something you need to make sure of, that the two zone axes are parallel to each other by less than 1 degree. And then this is the first one. And then the second one, if you do TM, you need to be sure that your grain boundary is edge on. If it is not edge on in conventional TM, you will get a whole zone of weird looking stuff. So that's the second thing.
Yeah. Okay. Thank you.
Sure.
Yeah. Subhash.
Hi, Nico. It's a very good,
Hi.
nice presentation. Hello, am I audible?
Yes.
Hello. Yeah, yeah. So I have two questions, basically from slide 16. This,
Yep.
yeah. So you're going to crystal in 001 direction, but why it specifically forms sigma 5 boundary? Means it can form sigma 3 also, but why it's specifically forming sigma 5 boundary? Because it's energetically favorable or other things?
Yes. So we set up. So this, yes, it can form a sigma 3, and we did this also already before. However, the sigma 3, you need different zone axes. So it depends on how you arrange the seed crystals. Depending on how you arrange the seed crystals, that's how you determine what grain boundary you will grow. It's not necessarily always the exact one. As I said, it's sometimes hard to predict what actually forms. But in principle, if you set up the two seed crystals correctly, you can determine what grain boundary grows. And we did this here with the 110 growth direction, 110 zone axis, which is the one, which is the tilt axis of the sigma 5 grain boundary.
Okay. Okay. So you are orienting this 56-degree beforehand, means two seed crystal in 56-degree, and it's actually forming sigma 5 boundary.
Exactly. So if you go back to this graph here, so the 54 degrees orientation here, that's the sigma 5 orientation. If you would rotate by, let's say, 20 degrees or 22 degrees, you would probably form a sigma 13 boundary.
Okay.
Does that make it clear?
Yeah, it makes clear. There is another sigma 5 boundary between 13 to 14, 30 to 40.
Yes.
That also we can make by arranging 30 to 40.
Yes. So that is now a good question. So if you, as I said, the one is a 210 and the other one is a 310 grain boundary, and the structure is very, very similar. I have never tried to grow both of them and see if they form how they should form. But in theory, exactly, if you rotate by 54 degrees, you should form the one variant. And if you rotate by 36 degrees, you should form the other one, in theory. But I've never tried it experimentally.
Yeah, and that's energy is very different. It's mostly minimum. And in that case, whether the behavior is same or not.
Yes, exactly. So this boundary is very special here. And so there's another plot, and let me see if I have that actually in the backups. Yes. So if you look now, this is the inclination angle, not longer the orientation angle, going from 0 to 45. And this is basically going from the 310 boundary to the 210 boundary. So you can see that the 310 boundary has a little bit lower energy than the 210 boundary. And this is all the asymmetric rotations that you can have in between. So you have both zone axes, or you have the 210 boundary with both grains oriented in 36 degrees. And now you rotate one relative to the other, right?
Yeah.
And then you record the energies and you get this curve. So you can tell that all the asymmetric boundaries have very similar energies, a little bit higher than the two special boundaries, so to say. And we are somewhere here with our boundary. So the way towards, the 210 boundary is not so far. And this is what I mentioned before, that this is why probably it likes to go there eventually. But does that answer your question a little bit more?
Yeah.
Yeah?
Yeah.
Super.
So I have another question from slide 18.
Yeah. Yes.
This is the lower one is atomic image is estimate. So why it's showing different contrast? Because it's a same, it's only atomic contrast. So why two copper side is showing different contrast?
You mean why these atoms have a different contrast than these?
This is silver. I can understand it's higher atomic, but both copper side, this lower grain and upper grain, the copper.
Yes. Ah, you mean in these images why this one is brighter than this one?
Yeah.
Yes. Okay. So the HADF condition is a mass thickness contrast. Means that if you have a higher Z number element, it's bright. But also, if the thickness is different for a certain area, if it's thicker, it's also brighter. If it's less thick, it's also less bright. There's another one, because this is just theory, based on pure theory. Now we do have an experimental detector, and we need to have the detector it's an annular detector, right? So there's a hole in the middle, and we only detect the very far diffracted electrons that hit the detector. So depending on how we choose the angle, we always have still diffraction contrast in our images. And this is very small, but this is there. And especially in STEM, if you have two grains that are not perfectly in zone, or one is perfectly in zone axis and the other one is not, then the one in zone axis is brighter than the other one. And the more you get out of zone axis, the less you will see until you only get a gray, some background. So probably in these two images, there was a little twist component of the grain boundary of the two grains relative to each other, and this one is not perfectly in zone axis. If that answers your question.
Yeah. And in next slide,
yeah,
this 2D profile of this faceted grain boundary what you're showing. In this image, it's showing that in asymmetric boundary also there is a concentrations of silver. This
in here you mean?
Yeah, here. Even for higher sections, means this flat section or coherent sections or symmetric sections, it's not showing the concentration.
You're a very good observer. Yes. So with atom probe, we have a problem because we don't see the atomic structure. Also, atom probe has a very good advantage or a very good resolution in depth. So along this line, going down here, but laterally the resolution is pretty bad. And this depends on the reconstruction that you use for your atom probe tip. Okay. Because of the curvature, eventually some atoms, you need to know where the atoms come from. And typically, if you have a grain boundary with some segregants, for example, silver has a different aberration field than copper, so it does different things. So in these lateral dimensions, I would say there's always a local blurring and a little uncertainty where atoms come from. Okay. So to be very honest with you, I don't really know where this comes from, but there is so much we can do about it. The good thing is we do observe the faceting, which is nice in atom probe. I would have not guessed to see it based on the dimension of the faceting. However, therefore, we do the highest structural resolution in TM, where we do see exactly where something sits. So the APT is more or less the confirmation of the chemical species and how much we have. That we see the faceting as well is just a plus for us.
Okay. Yeah, thank you.
Mm-hmm.
It's okay. Thank you.
Yeah.
Yeah.
So if there are any other questions, technical questions for Nico? I don't see any more raised hands, so maybe I will ask the last sort of technical questions.
Sure.
So again, since most of the people covered the things that perhaps Arjun covered, what I wanted to ask about if solute atom changes, then what happens and so on. So I would rather ask, what do you think are the consequences of this work? in terms of engineering applications, or in terms of even designing grain boundaries? Where do you think that this would lead to?
Yes. Well, so I think I think the nice thing is that we know now these transitions occur, and I think there has been plenty of studies that show, you know, these transitions are real. Not necessarily only the chemically triggered one that I showed today, but for temperature, in principle, they should be occurring for all the thermodynamic parameters, like pressure probably would help, and so on. So it's secure, they are there. So for me, the question remains, so what are they good for? And I think this is work that has rarely been tackled. Some people talk about abnormal grain growth is related to these transitions, that some grain boundaries have a different state, and therefore they, you know, have a different migration. But this is more based on, let's say I take a polycrystal with small grain size and then anneal it and see what comes out. There's not really the direct evidence, you know, this transition or this whatever phase transformation of a grain boundary has this and this property change associated to it. And this is what we tried with the mechanical stuff a little bit to, you know, we know it's this grain boundary, it does this transition, these are the features that are now coming up, and this is what happens because of it. And what we see is, for us, for example, chemistry is not the critical point. Like, however you can transform your boundary to have these facet junctions, that is probably a thing that might lead to change in mechanical properties, for example. So I think the main focus should now slowly switch towards, okay, relating these phenomena that we see, and there are some really interesting and cool ones, to, okay, what is happening? What are electrical properties? How are they influenced? How are whatever properties you want to think of? How are these related? And I think if this is exploited a little bit more, then you might start giving guidelines in a sense of grain boundary engineering or something like that. But at the moment, for me, I think this is a little bit too early to say, you know, you have to do this and that to get this and this result. I think there's just not enough knowledge on what can happen and what influence it can have. But I think this is the very special and interesting part now where we are, that we can actually exploit this and then come to the point where you can say, okay, now we know if you form these and these grain boundaries, it's much better. Right. But I also think it's important to see that not everything that we think we know, because we look at it in SEM, EBSD, or even TM, is necessarily how it looks. If you look at it in detail, it might be completely different, and that obviously changes, of course, sometimes your explanations why things happen and how they happen. So I think that's also a point people should pay more attention about, like, you know, looking more carefully in detailed locations, in very locally digging in what is happening there. Not saying the rest is not good, you know. It's also necessary, of course, but if you want to get to a point where you can make predictions, I think it's necessary to really get more of a broader sense here, what can happen.
Exactly, Nico. I think as also someone who finished his PhD pretty recently, you would have experienced that, right? That you go into a depth which nobody has in the field that you have, you know, chosen to work on, and that makes a difference to the understanding. And then, of course, then a lot of other people have to take it up and work around it to really explore and find where else it could head. So in that context, also, I had a few questions, like I said, generic questions about, you know, how you arrived at this particular PhD problem, and how is the process of, you know, defining a problem in MPIE or in your own experience. And I would also request if students had these questions, I mean, master students or PhD students, who are right now in different stages of their own student life, to ask these kind of questions. And Nico has promised to be around for a bit more longer. to answer that. So I asked this question already, but students who want to stay back and ask these questions and or listen to us, please feel free to again raise your hands. Yeah. Can you just tell us about this journey where you, I mean, how did you arrive at this particular problem to solve?
Yes. Yeah, that's, I mean, you said it basically. You dig into stuff, and generally once you dig into stuff, I mean, you know it, right? You always find stuff that you cannot explain, and then you keep digging and digging and digging and digging, and more stuff that you cannot explain comes up, and more and more and more. So no, I mean, I think from my PhD experience that I had, it's I was confronted by my supervisor, Professor Dehm, with a topic who said, well, you can look at grain boundaries in a TM. Do you like that? And I said, yes. And so you start learning the technique, right? You take some images of grain boundaries to learn the machine and all that. And there already questions usually come up. And I see that now with almost every PhD student that is around and doing grain boundaries here in the department. With the first initial training samples that you have, you already find your questions. And sometimes that's pure luck. Something nice comes up because you're just lucky. Sometimes, you know, you see something and then you think about it and you have some discussions and you find out, well, if I do this and that, you know, it might lead to this direction. And that's the best case because that is actual science, I would say, rather than having been just lucky. So I think there's so many ways. It's pretty hard to give a general thing. For me, I think I was quite lucky, I think, at the beginning because I was the first who was asked to look at grain boundaries in the department. And then I made a lucky choice with silver to put silver and copper. So I think in this regard, I was lucky. The rest is then you need to work, right? It's a lot of work. You need to go back and forth and back and forth. Sometimes things don't work and machines get broken and stuff like that. But once you have the main idea settled, the big idea, I would say, then the rest will just come normally because you have your supervisor, they have ideas, you have ideas. You go to conferences, you have people invited that might give you different perspectives. So along the way, ideas will always come. I think that if ideas during the way don't come, that's not usual.
Yeah, very, very well said, Nico. That it's always an individual story. It's a unique story for every student who starts out. But very important thing that you also said is that you have to keep working and going back and forth with it, even when something clicks. Sometimes things don't click right in the beginning, but when it does as well, you need to really, I mean, the kind of things that you had to learn and pick up along the way to be able to do this kind of work, you know, a lot of background researching and reading and everything of this kind goes into it. So that's probably...
Yes, but as you say, I think this is the more or less standard kind of thing, right? So you have to do that because also your boss wants to do that and you're encouraged to do that and so on. But from yourself, your intrinsic motivation, I think the only advice that I could give is if I wouldn't have been like proactive, meaning like I would just go to my advisor and tell them, hey, I would like to do this and that. I would like to go to China. I would like to go to the US. Is there a possibility? You know, a lot of people or I found along my student colleagues as well at the time, a lot of people are afraid of doing that for some reason. But if you don't go to someone and tell them what you would like to do, they would probably never know, or they don't have the time to know. So that might end up in a state where you think, where you lose chances just because you didn't speak up. There's nothing bad in saying, oh, I would like to go there, or I would like to do this, or I would like to use this machine. The worst that can happen is you get a no. But that's then that's then a no. That doesn't hurt you. But in most of the cases, people are very willing to help you, and then chances open up. And I think this has been, if I look back from the beginning of my undergrads to now, I think I have always been with people that were very supportive and opened up chances for me, sometimes because I asked, sometimes because I was just lucky again, sometimes because I got to know someone at a random conference, or I don't know. So these things, I think, are very important for someone to learn very early, because the early years make a little bit how you get out of your PhD, right? Who knows you? Who have you interacted with? Look, I wouldn't be talking to all of you guys if I wouldn't have been here with you.
That's true. That's not true, actually. Guru actually read your paper and he knew what.
Okay.
No, I
Okay.
just
Okay.
meant, I just meant that, even in addition to, knowing each other, Guru and his group do these simulations, which look at grain boundaries a lot, phase field in particular, and he really liked your work that you published recently, and he asked me whether I knew you, and that's how. So that apart, that was a very good point, and I think I had a student who said this in different words. I've seen him put up a status message which says, if you don't ask, then the answer is always a no. So
Yes.
that's really the important point, that you ask, and then, if the answer is still a no, it's okay, but you have nothing to lose. But you might have a lot to gain if you do. And
yes,
that
exactly.
leads me to probably the next question. From my own end, it's almost like I'm interviewing you, but there are students who are listening in. So
I know.
you have been all around, right? You've kind of visited 3 different continents, let's put it that way, during your from your journey from the UG to the PhD. So how was these, how different were these experiences? What did you find which was great? And the reason that you got back to Germany, was it more of a personal decision, or was it something that's also keeping in mind how things go and how things work there?
Okay. Yeah. So this is then the very personal questions now.
Oops,
How my
I'm sorry.
personal. No, not in a sense it's bad. My personal way of how I went
Right.
through my study stuff. So yeah, I was an undergrad in Saarland, and in I think the 3rd semester or so, I had a lecture which was called micromechanics. And it was not micromechanics in the sense that we would talk about it, like, mechanical properties. It was about MEMS-based devices, like actuators and stuff like that. So the professor there, I found him very inspiring, and the lecture was great. And, it was so much fun and interesting. And I don't know, I decided to go to him and just right away ask him, because we were not so many in the class, to ask him, hey, is there a chance maybe, do you know someone who does this stuff in the US? I would like to go abroad for a semester. Do you know someone? And well, he was a very nice Bavarian guy, very fat. He liked drinking beer a lot, but super nice. And he told me like, hey, sure, you can do a semester abroad, but I don't have good contacts to the US. I rather have good contacts to China. I was like, okay, China is random. Never thought about that. Sure, we'll see. And he right away mentioned, well, I have a summer school coming up in China, together with one professor there. And if you would like, I take all my students. If you would like, I would just take you as well. So, he paid for everything. He paid the flight, he paid the housing, like everything was paid for. And I was like blown away. That was just amazing, because in this way, that was the getting to know the Chinese culture, and it was like, I think 2 weeks, 1 week or 2 weeks. And I thought I could make up my mind. Do I want to do this for like a longer term or not? And we ended up, I liked it. So the professor there was super nice, and everyone was super nice, and the university environment was cool. So I decided, I talked to him and we decided together that it would make sense to write my bachelor thesis there. So my bachelor project was actually done then there for 3 months. That's how I got there. But I'm still in very good contact with the professor there. She's a very super nice woman, and she opened up a whole new possibilities. Obviously, I was able to go to conferences to Taiwan and things like that. So it was a great experience. And then I came back to Germany. I started my master thesis, my master studies, and at the time I started working as a student researcher, like here as a Hebe, like a student helper.
Intern, yes. It's called an
student intern. Yes. So I was working like that at the Leibniz Institute for New Materials with Professor Arzt, and I didn't get to interact a lot with him, but I should mention I applied there for a research exchange to Berkeley. No, not to Berkeley, to UC Santa Barbara. And I got an interview and I failed. Like, I was too young. They said you could come, we will interview you. And I failed. So they said your experience is not enough in the field that we require, and blah, yeah, yeah. So this is also an experience where it didn't work, like where I was just, where it was just a no. But I kept working at that institute and I did my job, and that's when I started getting into mechanics a little bit with Andreas Schneider also. And eventually it came to a point where I had to write my master thesis, and I just walked up to Professor Arzt. I met him maybe 10 times before, and so he's that big guy. He's like this legend, and so I was a little bit nervous, to be honest, but anyways, I just wrote him an email. The good thing was, at the time I was organizing a student conference and the institute sponsored it. So it went pretty well. And I wrote a summary email to him like, hey, this is how it went. Here are some pictures and this is for you. And thank you so much. And he said, well, that's awesome. If you need something, let me know. We can arrange. So, and then I thought, well, this might be the chance to ask him if there's a chance to go to the US. And indeed, he got back to me and said, yeah, I have very good contacts to the US. Here are some choices. What does suit you better? I can just send emails. And no joke, he sent emails to, I think, 7 of the top places in the US. And out of 7, I think 5 came back with like, yeah, sure, your student can come.
Yeah.
So that's pretty much how I ended up going to the States. And then the master thesis for us was like 1 year. So I again did my practical work, like my master thesis work in the US, which was also nice for me because if I would have done a semester, I would have needed to study, and that would have involved more funding and all that. But like this, I could just, it was more like I got a reimbursement and could just work there. And that was super easy in terms of visa and all these issues. So yeah, that was the US part. And then I came back to Germany again because I had to finish my master in like writing the thesis up and all that. And then I decided, because of him being so nice, sending me abroad 1 year, I stay in Germany with him for my PhD. But there were some issues why it didn't work out. The topics were a little bit off, and some people in the institute were not so interested in the topics he wanted to tackle, and so on. Long story short, I decided to move on, and I decided to go to Switzerland or to Düsseldorf. So I applied at ETH Zurich and here in Düsseldorf. And maybe you remember Sriram.
Yes, I do, of course.
Yes, so he was actually the guy who convinced me to do
That's wonderful.
here at MPIE.
I see.
Because he introduced me to the old, actually just the old TM, and it was just fascinating with the 6 thingies there. So I was like, okay, this is nice. People were nice, and at ETH, for example, I didn't feel the city was a little bit cold. People were a little bit colder. In Düsseldorf, when I went to the interview in the city, I find the people much more open and, a little bit nicer, which is again just the gut feeling, right? But in the end, I decided to go to Düsseldorf because of that, and there I stayed. And then, you know, Chris had contacts to Berkeley, and that's how suddenly I could end up writing a proposal to go to Berkeley and stayed there for 3 months. So it was always like asking and having some luck associated with it, or things like this. So this is how this evolved, and I'm here now, and I wanted to go abroad again. So I would have liked to have the experience of India as well.
That'd be great. We will
yes.
invite you the next time that we can, at least for a visit.
Yes, I would
I'm
love
sure,
to.
yeah, being your adventurous self, you will enjoy it.
Yes, absolutely. So for me at the beginning, when I went to China, I said that's an adventure. I have never been outside of Europe. That's an adventure, and it was an adventure. It was like literally something new every day. And then I said, well, now I know the one side of the scientific world. Now I want to see the other side of the scientific world. So I want really to go to the US. And as I said, like India is kind of missing. That's the last kind of big thing that I want to do. But for my postdoc now, I thought about going to the US, back to the US actually, to Berkeley. But then COVID hit, and you know, then things just got complicated. So this is why I then looked around. And yes, and because of, you know, Steffen Brinkmann. So he went to Jülich. So he, during Christmas time, he sent me an email like, hey, what are your plans after your PhD? We are looking for a postdoc doing this and that, and potentially a group leader. So maybe you can just write an email to Ruth Schweiger.
Right, makes sense.
This is not my preference, certainly not, but because of Steffen, I would just send an email and be nice, you know, polite. And turns out it was a super nice package. Like,
Great, awesome.
like, yeah, like the interview was super. She's super supportive. So everything worked out great. And again, it's not that I was fixed on Germany, but it was just it felt like the right thing to do. Sometimes the gut feeling is better than the brain, for me at least.
Yes. Thank you so much.
For the experiences, China was amazing. Like a completely different culture for sure.
Yes.
But scientifically, so they work a lot, like a lot.
That's right. They're really known for working long hours and hard,
yes,
like really hard workers. Yeah.
But the US was the same. The US was also, they worked a lot.
Yes.
We actually bought I remember with my office mate, we bought a couch for our office, a sleeping couch, so that in the late nights we could eventually sleep in the office if you wanted to.
Yes.
So there we also worked a lot. In terms of Germany, I think we are in a very comfortable environment. Like, as you said, work-life balance here is
it's really
excellent
good.
compared to other countries.
Yeah, I've been telling that to students who, you know, ask about the different experiences and different work cultures, that Europe actually has probably the best work-life balance that way.
Yeah,
so
I might agree.
You agree. So any students who want to ask anything to Nico? He was a student not so long ago, so you can feel a little more free.
Yeah, there's the activation barrier should be very low for this.
I hope so.
And I will certainly give honest answers. Like, you know, if you want to ask me how I was stressed out during thesis writing or stuff like that, that's all good for me.
Yes. Please do.
I have a question. Are these all students of yours now here?
No, there have been students from the department across different faculty here. Whoever was interested in this topic. We also, of course, advertise to other institutes, but mostly these students are from IIT Bombay. But many of them are mine. You might have, I don't know if you remember meeting Nitin George Mathis is here. And then Kevin, Deepesh, Rishikesh, and Bikash, they're also working with me. Ashwini is also here. So yeah, a lot of them did attend today, but there were more students earlier, and they were from across the other faculty as well.
Okay. I'm just asking. I'm really bad with names, so if I read all these names, you know, I need an image.
That's really all right. And understandable. Yeah, so
Cool.
if students have any questions, because we have taken a lot of time from Nico as well, please feel free to unmute yourself and ask. Okay, if not, I think I talk too much, so.
That's fine.
So
I mean, that's all good.
But it was really nice, Nico, to have you here and share everything that you did. Of course, your work and also these experiences. Students here can be quite shy of asking, but I'm sure they will benefit from listening to you and hearing you out. And I hope that at some point they really start asking themselves.
No, that's totally fine. That's always the same. I was the same. I was always also very shy in asking questions, so I understand that. But did I have? I think I had a question, but I forgot. Never mind.
All right.
Oh yeah, but it was
yes,
super nice.
Nikita, there's one raised hand. Do you want to
Yeah.
ask something?
Yeah. Sorry, did you talk to me?
Nikita, your hand is raised, but I don't know if you want to ask something. Yes.
It's not, it's more like a request, not a question, because I am like, I'll be working in like grain boundary only, and I would like to discuss. So if I can get your email or something, I just wanted to remind that.
I was just about to say, actually, like, if you have any questions or if you want to contact me, always, right? Like, Jaya, you know how to reach me. I sent my email address right here in the chat right now.
Yeah.
So feel free, you know, send me an email whenever. Just write in the like something like, "Hey, I saw your talk," and then I know.
Yes.
So anytime, of course, you can contact me. That's not a problem.
Yeah. Thank you. Thank you so very much. It has really been a an honor for us to have you. And
oh no. Come on. No, thank you so much for the invitation. I was very happy when I saw it. I was like super happy.
Thank you. And I hope that next time we'll actually see you physically here, coming over to IIT Bombay and visiting us and probably taking a tour in India. So
I would love to do so, for sure.
Yeah, another student, Surya, says your talk was very helpful. Thank you. So they put some messages there. Yeah. All right. That
cool.
We'll call it a day then, and see you the next time whenever we have a seminar. And Nico, I will see you whenever I see you.
Exactly. When you come back, hopefully I will be here. If not, send me an email. So I will come over.
I'll come over to your lecture and visit you.
Perfect. There's actually, we should actually talk because I will do a lot of in situ TEM deformation, and we got a new holder which is very special. It's the first holder in Europe, so we can do mechanical testing at very high temperatures at atomic resolution. So we can in the TM we can go up to 1200 degrees C, and but also do atomically resolved deformation at these temperatures.
Wow.
So that's fairly special. So we should, maybe you can remind.
Yes, I will talk to you about it. I'll ping you separately maybe, and we will talk about it.
That's fine.
If something is possible to be worked out, because there are some students, of course, whose work we have been able to do to a certain extent because we have certain facilities here. But like, Kevin was mentioning, we don't have a aberration corrected microscope. We still have a. So there are some things that are limiting us, and maybe if we can discuss and try to work some things out, that would be really good.
Sure. So I will be sitting at the Ernst-Ruska-Zentrum there as a bridge between the Institute of Ruth Schweiger and the Ernst-Ruska-Zentrum. So in terms of microscopes, I think I have access to almost everything that's there.
Brilliant. Yeah.
Yes. So there might be something interesting, but just so you know.
Yes. Thank you.
All right. Sure.
Right. Take care and then bye.
Yep. Bye. Bye, everyone.
Bye.